Yes, students, this lecture series is going to be on logic gates and logical operators. So we're going to basically talk about binary logic and the operations we can do on binary variables. So first let's start with what actually is a binary variable. So a binary variable is a variable which can take only two states, either high or low, as we've discussed in class. So in practice, we normally deal with decimal numbers, so the base is 10, and the symbols we use to create any particular number is from 0 to 9. So when the base is only 2, we can have only two such fundamental numbers, if you want, which we can use to form any particular number we want. So by combining zeros and ones, now we can create any particular number. So the way we actually create numbers we discuss later. Okay. Now, what are the logic functions that we can do on these binary variables? So they're listed here. We have OR function, the AND function, the NOR function, and NAND, NOT, XOR, and XNOR, which we're going to look at subsequently. Now, the approach we're going to take in this chapter is something called behavioral description. So, behavior description is an approach we take where we treat all the symbols or the part of the system we are considering as a simple block diagram, which is hidden to us, and we're not interested in what's actually inside this box, but what is the behavior of the system. So that's what we are interested in. Okay, so a simple example is given here, which will be shared, of course, to you to describe. For example, if you take this block here with two input pins in and P/N, and we have an output count, so we could explain the behavior of this block here based on the states of in and P/N and how the output count varies. So the behavioral description approach here would not actually look what's inside this block to describe how the circuit works, but it's just in terms of its behavior. Okay, now coming back to the binary variables, like we said, they only take two states. So because they have two states, it's 0 or 1. Because the base is 2, this is why we have two states. If you are considering any particular logical function, and if you have only one variable, so the number of combinations is 2 power 1. So you get two possible combinations, 0, 0, 1. If you have two variables, each variable can take 0, 1 alternatively. Yeah. So individually, separately. So this leads to 4 possible combinations, which are listed here: 0, 0, 0, 1, 1, 0, 1, 1. And so these 4 states actually, which are obtained by combining the states taken by inputs, is 4, and this is 2 power 2. Now, 2 in the exponent here is the number of variables. So similarly, if you have 3 variables, the number of states you can have is 8. And these are the states here: 0, 0, 0, 0, 0, 1, and so on. Now, if you just list it like this, it's not very useful. So typically we list a table, which is known as truth table. So here we are listing the possible combinations for 4 variables. So we get 2 power 4, so you get 16 possible combinations. Now, this is a very systematic way for you to go about listing all these combinations. So these 4 columns you find here are all inputs. We are not dealing with the output at this point. We're just dealing with the combinations of the input. So you can see you have 16 rows here, and how do we go about giving these states to these different rows so that you don't miss any particular combination is very simple. So in the rightmost column here, you just alternate the state of A, in this case, for every single row. Then to the left, you get B. So this one alternate every 2 rows. And now to the left again, you get C. Now it's every 4 rows, and then every 8 rows. We just keep doing that. We find that we get all the possible 16 combinations. Okay, so let's look at the risk gates now. The first one is the OR gate. So it's a symbol for the OR gate, and this is a 2-input OR gate. We just discussed if you have 2 inputs, it means 2 power 2, you get 4 possible combinations. These are the 4 possible combinations that we have in the in this particular case. Yeah, these 4 possible combinations are shown here. Yeah. So irrespective of the logical operation you are considering, these 4 combinations would be always there for 2 inputs. I can just say. Now, for the particular gate we're considering now, the OR gate. Okay, the OR gate in terms of behavioral description, this is given here. So the output Q of OR gate is high if at least one of the input is high. So if you look at the truth table now, we find that for the 4 combinations here, if at least A or B or both are high, then the output is high. So we have only one possible combination, which is 0, 0 here, which the output state is 0. So mathematically, we can represent the operation as a plus operation. So that plus here is not what we typically do in arithmetic on decimal numbers. So when we talk about Boolean algebra, this plus here represents the O function, and it can be lightened. So one way you can just going to erase this. So it can be likened to the plus operations. So in a way, it's a mnemonic for you if you want to remember the operation. So one way to do it is as described here in terms of behavior description. The output Q is high if at least one input is high, but you can also remember the operation as an addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 would not be 2 because 2 doesn't exist in binary, is going to be 1. Okay, so the next logical operation which we consider is the AND logical operations. Again, of course, the AND logical operation would apply on binary variables. So A and B here are binary variables which can take only 2 states or 1. So I'm stressing on that, it's very important. So Boolean algebra is a set of operations on binary variables. So in this case, this is the logical symbol, for the AND gate. Again, because with 2 inputs, it could be more than 2 inputs, but it cannot be less. It can't be just one input. Does that make sense? So when you're ANDing, you should get at least 2 inputs. It can be 3, can be 4, can be more. And just a behavior description here. For the AND gate, the output Q is high if both inputs are high. So if you consider the truth table again, you can see the combinations of B and A are very similar to what we had for the O operation. So we have the 4 combinations, and based on the behavior description for the AND function, you can find that only the last row here where both inputs are high do you get actually high for the output. All the other 3 combinations here would give an output of 0 or low output. So the way we can represent the AND operation is by dot or multiplication. Again, this is not the same as the arithmetic applied on decimal numbers, but it is analogous, as we'll be saying. So one way you can remember the operation of AND gate is based on the behavior description here. So all the inputs, in this case, you have 2 inputs. If you have 3 inputs, all the 3 inputs would have to be high for the output to be high. The mnemonic to remember it now, just like we did for the operation was addition. Here you can just multiply. So 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. So that's another way you can remember the operation of the AND gate. Next, we look at the NOT gate. So NOT gate is a unary gate. In this case, you have only 1 input. So it's just an inversion. It's a very simple gate here. You're just inverting the state of A. So if A was low, Q will become high. If A was high, then Q will become low. So the behavior description is simply this output is simply the opposite logic state of an input. So since you have only 1 input, you have only 2 combinations here, and the output is just the logical inversion. Now, mathematically, you can represent it like this. So you're complementing, you have a bar on top of the variable. So this means complement. Now, if you go back to the symbol for the NOT gate, so normally shown a triangle, but we'll be seeing in the other gates we're considering, the inversion is normally represented just by this small circle here. So if you're considering, of course, a NOT gate on this triangle as shown here, but when you're combining the NOT gate with other gates, it can be shown just as a small circle, like in this case here. So next gate we consider is the NOR gate. So this is a NOT OR gate, as you can see here. So it's OR gate and invert it. So if you combine these 2 symbols here, you just put a small circle here at the end of OR gate, you get a NOR gate. So if you understood what the OR gate is about, it's just inverting the output. For the OR gate, you get a NOR gate. So I would invite you to do that. Draw truth table for the NOR gate. So in this case, you have 2 inputs. So you have 4 possible combinations. Remember, for the OR gate, you added O. For the OR gate, you said at least 1 input should be high for the output to be high. So in this case, you do the same thing, but then you just invert the logical state. Okay, so give it a try. At all. The next gate we consider the NAND gate. So you would have guessed it, it's a NOT AND gate. You take the AND gate and then you invert it. So again, you can construct a truth table for it. The symbol would be as follows. We just draw this one for you. So this one was the two input AND gate. So this one, like we said, you just invert it and you will get your NAND gate. Yep, so nothing difficult. So I would invite you again to do the truth table for the NAND gate. So again, you have two inputs here. So remember, for the AND gate, you multiply two inputs, or in terms of behavior description, what we say is both inputs should be high for the output to be high. So in this case, we want both inputs are high, the output to be low, and all the other combinations actually high. So again, try to give us a try and construct the truth table for it. Now, the next gate we consider is called XOR gate or exclusive OR gate. So it's very similar to the OR gate. You can see here the symbol has OR gate, but then we have this double curved part here, which is saying it's exclusive OR gate. So the only difference here, if you look at the truth table, is in the last row here. So when both inputs are high for the OR gate, this will be high, but this one is low. Okay, so it is exclusive OR gate in the sense we're saying only one of the input can be high at the time. When both inputs are high, like in this case, the output will be low. Another way to describe the operation of this gate is that when the inputs have different states, we have different states here, B is 0, A is 1, or B is 1, A is 0, so have different states, then the output is high. So this is also a difference gate, as you can see clearly here. When both inputs have different states, the output is high. When both inputs have the same state, the output is low. Now, mathematically, it can be represented as follows. So we have the plus, and then we just circle it to show the exclusive operation. Okay, now the next gate we consider is XNOR gate. So to be the XOR gate, and then just invert it. So if you want to draw a symbol to be exactly as this one, but with a small circle at the end here to say we are logically inverting the output of XOR gate to obtain XNOR gate. So if you construct now the truth table, so to give it a try to draw a symbol, and then next you write a Boolean equation using the XOR and XOR and not logical operations. So it's just going to be this expression here with a complement on top. That's your mathematical representation. Now, if you do the truth table, it's going to be exactly the invert of this one. So this one will be 1 here, 0, 0, 1. Okay, so if you do that, then you'll find now if you want to give a behavioral description for this gate, it's simply going to be when both inputs have the same state, the output is high, and when states of the inputs are different, it's going to be low. So in this case, it's called a parity gate. So XOR gate is known as a difference gate, and XOR gate is a parity gate because that's the opposite. So next, we look at sort of a topic in digital electronics known as combinatorial logic. So we are starting to combine logical gates to obtain a particular logical function. Yeah. So once we understood how each individual logical gate operate, we can start combining them to obtain new logical operations. Okay. So this is a very interesting domain which we're going to look at, and a very powerful domain as well. So you can create new logical functions which can't be achieved with individual logic gates themselves. So let's take this example here where you have this A and B as inputs, and what you have as output is Q. What is written here as C, D, E, F are not actual inputs, no outputs, are intermediate states that we actually label so that we can construct the relationship between A, B, and Q. Okay, so in this case, since you have two inputs, we have 4 combinations as we've seen earlier. So this B and A here are actually your inputs. I just annotate that. So these are your inputs only. And like we said, C, D, E, F are intermediate states. So like we've discussed earlier, you have 2 power 2, so you have 4. So you list all the possible combinations. Then let's start finding C, D, E, F, and ultimately we can find Q. So let's see what is C actually. Okay, so if we look at C, we find C is the opposite of D. So we're just inverting A. So you can see here to find C, you just invert A. So 0 is 1, 1 is 0, 0, 1, 1, 0. So you found C. Similarly, now D is the logical inversion of B. So just invert B. So 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0. So you got your D. Next we find E. So E is the logical ending of B with C. So multiply B and C. Just multiply B and C to obtain E. Yeah, so B and C. 0 times 1 you get 0, 0 times 0 you get 0, 1 times 1 you get 1, and 1 times 0 you get 0. Next we find F. So F is again the logical ending of A with D. So A and D you multiply. So 0 times 1, you get 0. 1 times 1 you get your 1, 0 times 0 you get 0, and 1 times 0 you get your 0. So once you find your E and F, now finally you can find your Q, which is the logical operation between E and F. So we've seen the logical operation is addition basically. So we can just add these two now. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 0 plus 0 is 0. So if you look at the overall gate now, we can forget about C, D, E, F because we know they were intermediate states. So if you look at B, A, and Q, you find that when B and A are 0, 0, you get 0. When it's 1, 1, you get 0. But then 0, 1, you get 1, and 1, 0, you get 1. So we have seen this gate already. It's XOR gate. How you could implement the XOR gate using the fundamental gates like AND, NOT, OR gates. Okay, so it's an exercise for you to work on now with different combinations of gates. In this case, you have 3 inputs A, B, and C. So in this case, you would have 2 power 3, 8 possible combinations. So it's up to you now to put this into intermediate states where required. Typically, they are the output of your logical gates. And then construct a truth table and calculate these intermediate states. So finally, you can find Q. Next, once you've got the truth table there, I've given here to you a small timing diagram here. So based on the truth table, you should be able to find. For example, in this case, we are asking you when A is 0, B is 0, and C is 0, what state do you take, which will find the truth table. Similarly, if you take instances, so as you look for this time diagram, wherever you have changes in states, this is 0, 0, 0. At some point, it becomes 0 for I. Then for B is 1 and C 0. So you have to look in your truth table for this part of your combination, what output you get. So this is again an exercise for you to work on, which we'll discuss in your tutorial class. Okay, so I'm going to stop here. I'll leave it to you to work on the examples I put here in your handout as self-practice, and we'll discuss this further. So as you can see, the next video I'll be sending is on Boolean algebra, simplification, problem formulation. So this is an area, a chapter where we're going to now start dealing with logical expressions as mathematical expressions. So one important law for us with De Morgan's law. Okay, so that will be the subject of the next video. I thank you very much for attention. So do work on the examples, on the assignments, on the problems I've discussed here, and we can take this up in class. Thank you.